everyone is asking now. Two thoughts came to my mind. Number one was to be a banker. That was what I wanted to be right from the start. But I ended up in the engineering career because partly the main reason was because I was offered a chance with EDB on a scholarship program to join the semiconductor industry. So that's how I ended up with the semiconductor industry. My first career was starting in the semiconductor industry. So REC came to Singapore and I found this opportunity with REC. To be frank, it's a manufacturing line, so it's quite similar. It's just that solar process is slightly not so complicated like the semiconductor process. But it poses a lot of challenge because the solar industry is at its infant age. So having reflected back between a technical career or maybe a possible banking career, I think that a technical career is something that is very interesting to me. I get to learn and apply what I've done in the university. As I mentioned, my background is in electrical engineering. So every moment, as I look at the processes, is what I've learned. I can apply what I learned directly to from the textbook into the practical working world. At the same time, as I progress up the career ladder, it becomes a little bit like a business world to me as well, because all businesses depend on cost. So I actually have to work a lot on cost. I will work to bring down the manufacturing cost. I will work to think of how to have innovative processes to bring down cost. And at times I have to deal with suppliers, my suppliers to bring down cost as well. So to some extent, a technical career offers that. So this is a slight introduction of myself. I'll give you all a slight introduction of my company, REC. Our mission statement, by the way, REC stands for Renewable Energy Corporation. Our mission statement is to provide smart energy for a greener future. Our vision is to be the world-leading provider of highly competitive solar energy solutions. One very positive point about REC is that we are very much integrated company. What I mean by integrated company is that we produce from silicon, that's the basic raw material to make a solar cell, a solar panel, all the way to putting it on the field, as in hooking up the system in the field. So we are doing everything from scratch to the end. And this gives us a competitive advantage because we are not having any other suppliers who will determine our future. For example, having come from the semiconductor industry, because typically we don't make raw wafer. So as we do not make raw wafer, we are very much susceptible to the prices of the raw wafer supplier. So whenever they increase price, we will be in trouble. Trouble means our operating profits or operating margins will reduce. Whereas now in REC, I see the full benefit because from the start to the end we do it. So we can drive costs very well down. As mentioned, we have the presence across the solar chain, value and this creates strategic opportunities. And one of our key motto is for cost reduction to give the end market a better price. This is REC in Singapore. We are situated in Tuas. There's a very nice sea view. I would say it's close to a 270-degree sea view. All around us is actually the sea. And in fact, we can see parts of Malaysia and Indonesia at times. So it's quite a nice view, especially during lunch. So this facility was actually opened in the November 3rd, 2010. It was actually quite a big event. We managed to get our Prime Minister, Mr. Lee Hsien Loong, down to visit us. And take note that this was close to a $2.5 billion that the Norway parent company has pumped into Singapore. We are very thankful also to the EDB officers who actually brought REC to Singapore. This created a very nice working company and a very good job ahead for a lot of us. This is where I work in. This is a cells building. I'll go through later what exactly is meant by a cell. Just some solar industry update and development. This was something that Thomas Edison told two of his friends, very familiar, Henry Ford. I believe a lot of people should know who Henry Ford is, and Thomas Edison. So he said that if I were to put my money on the sun and solar energy, what the source of power it will be. And I hope that this development then will not run out until oil and coal has run out. So this Thomas Edison, which is a very good guy who invented the light bulb basically, he really has a vision that actually solar energy is the way to go. It's just that at the moment of time, it could not be harnessed into real electricity. Why is there such a big demand for electricity? If you look through the years, from the year 2000 to 2100, I guess I won't leave until then, but then look at how much solar energy is expected to project to. Look at the enormous potential of solar energy. This is how solar energy is compared with other sources of energy. Basically, oil and coal, natural gas, we will eventually run out. But as long as the sun is still there, every 12 hours or slightly more than that, we can harness this energy. Look at how big the cube is for solar energy compared to the rest. So there is more energy delivered by the sun in 1 hour that can be consumed by the world population in 1 year. You just need 1 hour of energy from the sun, and basically it can supply us the whole world, 1 year worth of energy supply. That's the power of solar energy. This is the oil prices, something that being in the manufacturing line is something very critical to us because it basically drives the cost of electricity. When it drives the cost of electricity, it basically drives the manufacturing cost a lot, and this is bottom line profits. So this is expected. How much is expected to rise? Within 10 years, it's expected to go to $1,000 per oil barrel. That's how expensive oil is. This is the cost of PV modules in the market. Basically, you can see in June 2010 is expected to be each watt peak at $1.7 US. This is how much this industry has dropped from the early days of manufacturing in the 1980s. It has dropped down so much. So it makes PV manufacturing something that can be appreciated, something that is worth investing in, because the cost of manufacturing has dropped a lot, which means the prices of electricity coming from solar energy is getting cheaper and cheaper. There's this term in the solar industry which we call grid parity. This is when the grid electricity or electricity coming from oil supply, uranium, coal, reaches the same stage as in the same cost of renewable energy, something like solar energy that we have. So we are expected to reach grid parity soon, and this will really drive the push for solar energy rather than depending on the old traditional oil industry set energies. Again, on REC, as I mentioned, the processes step, we start from basic silicon, we make the wafer, after we make the solar cells, and we form it to modules, and then we install in the market. So take note, the cost of a solar system is actually the total lifetime cost of this system divided by how much energy it can do. That is dollars in kilowatts hour. We look at the silicon technology now, how it works. So basically it's a chemical process. These are raw silicon ingots, and these are where we form the wafer later. I'll show you a process flow chart in a short while's time. We start with metallurgical grade silicon. Using a melting process, we form silane gas. Basically, there's two uses for silane gas. We can actually sell it to other PV markets because silane is being used as a raw material to make a cell. We can sell it to the LCD market and even for the thin film solar market. But in REC, most of the silane gas that we generate is actually going to a polysilicon process which forms the raw material for the cell. So we have this famous process known as Siemens process, in which it pyrolyzes the silane gas to form back silicon, polysilicon. The difference between polysilicon and monosilicon is that monosilicon is made from one crystal, it's very pure. Polysilicon, you will see a lot of different grains, because it's formed by many different crystals. Eventually, with the rods, we cut the pieces and load in the crucibles to form the wafer. REC wafer. This is how a whole big ingot looks like. There's two differences here. This is the monosilicon, and this is what we call polysilicon. Basically, on the monosilicon, you can see that it is one whole grain, one whole crystal by itself. Whereas polysilicon, you can see a lot of grain size is like looking like a world map. So the difference is that this is formed by a pure crystal. This is formed by melting of many silicon compounds, silicon alloys. So what we do is first we solar grade silicon. We'll put it into a crucible, a big massive crucible. We'll melt it in the furnace. After it starts melting, we start cooling down the silicon, and then eventually you will form one whole big block. And each block is actually cut into 16 ingots, and after which we will slice the ingot to form a single wafer. Just to give a figure, a rough estimation, one wafer is about 180 micron in thickness. So it's basically putting, I think, close to 4 pieces of paper together. That's the size of one piece of wafer that we have. The next step is for REC solar technology. This is actually where we start forming the final product, going to cells and modules. How does the solar cell work? So basically, it's like a PN junction. So what happens when light passes into the solar cell? It will generate an electron hole pair at the P and N junction interface. The electrons is collected by the prime grid. The holes are recombined at the N grid. So with the movement of the electrons, electricity is formed. How does the solar cell look like? So basically, this is the front of a solar cell. This is the back of the solar cell. On this front, why it's looking blue in color is because there's a layer of nitride, which is about 80 nanometer in thickness, so it looks bluish in color. And all these lines here are actually silver lines, pure silver lines, because they are very good conductor of electrons. So the electrons is actually all captured by the grid lines, pass into a bus bar, and carry forward into a storage area. When we talk about solar cell, we will always talk about this thing known as conversion efficiency. Conversion efficiency in simple language is just if you pass X amount of light into a piece of solar cell, how much will actually be conducted into electricity. So what are the causes of cell efficiency losses in the silicon solar cell? Basically, there's a few mechanisms. A refraction loss in which light entering the solar cell is being refracted out. There's recombination losses when impurities in the silicon itself causes the electrons to be recombined again. There's resistive losses. The silver grid does not conduct electricity as well. And there's thermal losses. So, back from the raw material, which I showed just now, from an ingot we cut into wafers. Basically what we do after that is to perform a layer of wet chemistry, etching. This is what we call the texture process, is to texture the process so that it is able to roughen the process to capture more light. Follow which there's the doping process. Basically, the doping process is to form the P and N junction. After that, we will deposit a layer of passivation, or what we call the anti-refractive coating. This is to passivate the surface of the solar cell, followed by